corresponding to the empty space, please.
Okay. Do you hear me well? Microphone works? Yeah? Okay. Thank you. I actually didn't want to give this talk, so organizers twisted my hands. Why I didn't want to give how to deal with graphene. You get a chunk of graphite and pull out, literally or figuratively, one atomic plane, and you forget about what's left on the scotch tape and enjoy studying this material. You can a little bit twist your perception and forget about graphene and ask yourself what is left behind. And schematically, what is left behind after you pull 1, 2, 3 atomic planes, it's an empty space in the chunk of graphite what is left. So, so the subject which I'm going to talk about is properties of this two-dimensional space which is left behind. So, how do we do that? Probably some immediately start thinking about the technique van der Waals assembly, which is very familiar to this audience. So you get an atomically flat two-dimensional crystal or flat surface, clean graphite. For example, one put 1, 2, 3 layers of another material, whatever you want it could be, boron nitride or molybdenum disulfide, and close it by a material of your choice, whatever you want to choose. So that's cartoon, but we managed to do these channels in reality. Here you see this is a slit, and this is only 2.7 angstroms capillary. This is graphite, this is graphite. Those spaces are here. Essentially, this is 2 planes pulled out of graphite, as I told you, although it's done by assembly. We never managed to get a decent photograph for monolayer to intercalate. If you wish, not only absorption, but also intercalation works. I said this important word now, absorption. This is why water goes there. So this is the simplest qualitative way to explain.
The question here?
Yeah, I have 2 small questions. You show situation when the channel is smaller than salvation shell for ions.
Yeah.
So I'm curious, is it possible that permeability is limited by the entry when this salvation shell must be partially destroyed? Because when it's already there...
I repeated in my talk twice that we checked it in an experiment, checking different lengths of the capillaries, that it's not entry and exit effects. Mobility, what we measure electrical properties, is dependent, yeah.
Okay. And then another one is epsilon 1.8. Is it close to just electronic components of epsilon?
We didn't claim 1.8, we claimed about 2. It's, you can interpret it a different way, but essentially it's your water molecule, it's like a dipole. So dipole sticks with one end to the surface, so it's already kind of polarized. So it's very hard to do more polarization than it is. It's out of plane polarization. You see, it's essentially polarized. If you wish, it's kind of ferroelectrical, right?
Well, ionic part definitely is saturated, polarized, but electronic still gives you this 1.8 or something.
Yeah, it's an optical.
Optical.
It's an optical polarizability. Yeah. Yeah.
Okay.
Yeah. You are right. Electronic.
Okay. Have you looked at the water transport through mica channels, and what is the slip length? Because there, it's atomically flat and the surface is definitely charged.
Sorry, I didn't get it.
Mica channels.
Mica channels. We didn't study gas